last night. Too soon to actually have them available for this press conference, but they'll be available very soon. So we're monitoring the weather. Every sol we're getting a weather report. We're watching the dust as it moves overhead on the lander, and we're starting to prepare for doing nighttime observations, which will tell us how the weather changes at night, and could be potentially very interesting as it gets quite cold and perhaps there's some frost or some surface fogs or something else that forms at night. We haven't been able to check yet. We're doing the first interactions between the robotic arm and the surface, and this is where things are getting really interesting. This is what the mission is all about. We felt we didn't need wheels because we're in a place where one hummock looks the same as the next as you look around the scene, and this is as good a place as we could imagine landing. We're ready to start interacting with the surface. We've done a touch test, and we've done 2 dig and dump tests. And this is where it's absolutely making me so happy. Let me show you the first picture. And this is after the second dump, dig and dump, that is. And if you look at the right-hand side of the picture, just above the shadow, you see where we've made 2 digging operations. This is only a scoop, a dump, a scoop, and a dump. That's it. That's all that's been done there. And yet, you see some whitish material in the upper area where the scoop has interacted with the surface. Now, for the science team, we've had an impassioned discussion about whether that might be more likely to be salts or perhaps ice or even some other materials that are more exotic. But I think salts and ice are probably the leading contenders here. And it's very difficult to tell which just because it's white. As you know, the Spirit rover used its wheel like a plow. It had a stuck wheel, turned around, went backwards, used it like a plow, and found very whitish material right near the surface, which turned out to be silica. Silica is important because it forms in hydrothermal vent locations. Now, we don't think we're finding silica here, but white material does not necessarily mean ice, so we're quite thrilled to be getting our first samples up to the TIGA instrument. The sample will be collected, let's see, I guess today, the Martian Sol 10. And the next slide shows where we're going to be picking up that sample. And this graphic has 3 locations, and we're going to be picking up 3 samples as we progress through the first cycle of sampling and delivering samples to the instruments. You see at the left location is called Baby Bear, Mama Bear, and Papa Bear. Baby Bear will be the first sample collected. It's right next to that trench that we've just dug, and it'll be delivered to the TIGA instrument. And if I can have my next graphic, the TIGA instrument has got its doors open, prepared to receive that sample. One door is partially open, but that's not going to impede us at all. We've done a series of checks here to be sure that the sample can be delivered into the oven. There's going to be no problem. So even though it looks like it's restricting the sampling operation, it's really going to have no effect. So this is where we're at today. We're getting our first sample, and at the end of this delivery, which will take 2 days, one to get the sample and bring it to TIGA, the next and verify that it's there. Then we have to see those images to effect that verification, and then Sol 11 will be delivering the sample, and Sol 12 will verify that it was received. So that'll be the end of our characterization phase and the start of our normal science operation phase, where we'll be moving into these national parks that we've defined and actually finding the best and most interesting places to dig trenches to understand this very interesting region on Mars. And to tell us a little more about our strategy for digging is Carol Stoker. Carol?
Okay, I'm going to describe our digging strategy. I'm going to use some visualization tools that help us to understand the workspace and hopefully help you to understand the workspace. So we're going to start with an animation that will allow us to fly in. So here we are, top down, looking down on some polygons with the lander in the middle, and then we're going to fly in towards the lander, and then you see a terrain in front of you that is the workspace of the arm. And to visualize this, we're using a software package that was built at NASA Ames called VIS, that is being brought to the mission to help us to understand the terrain and to plan the mission. And it's really a good tool for mapping. So the next slide now shows you the terrain that is the work area of the arm, and overlaid on that terrain is a pink area, and that's actually where the arm can access for digging. And then at the outside of that pink area is a green area, and that is reserved for the placement of an instrument on the arm called the TECP. And then off to the left side is a blue area, and that's essentially reserved for dumping. That's where the soil will be piled up after we dig it out of the hole. So the next slide now shows you, again, this beautiful color image from the SSI camera. And this is now two, as Peter mentioned, 2 scoops into the soil, and we see that there's a white layer becoming visible in the wall of that trench. And now if we go to the next slide, again, this is a view using VIS, and the top left view actually shows the trench with the robotic arm scoop positioned above it. And then the bottom view is a view down looking into the trench. And what we can do is use this terrain visualization to actually make measurements, sort of like you could walk around if you were on the surface of Mars yourself. You could walk around and see things from different angles and actually, put a ruler into the trench and measure how deep it is. And so we're putting a virtual ruler into that trench, and we're seeing that that white layer in the trench is actually only 1.5 inches deep. And I realized that I forgot to mention on the the slide that was the color image, we actually had 3 rocks in the field of view. And to give you an idea of how big things are, this is the size of those rocks in the field of view. So, about fist size. These are, in geology terms, these are called hand samples because they will fit in your hand. Okay, so now we'll go to my last slide. And this is, again, that terrain that has now had a color coating put on top of it that represents the elevations. So blue is the deepest elevation area, and red is the highest elevation area. And to give you an idea of just how much elevation difference there is across the work area of the arm, the difference between blue and red in that scale is about 15 inches. So from the deepest to the highest area is roughly 15 inches. We can put that graphic back up. So on the graphic it shows where our first scoop occurred. It's far to the left side of that area, and then we have a dotted line surrounding the work area of the arm. And the next sample, the sample that's being acquired today, is immediately to the right of the first scoop, and that sample will be acquired from the surface. And that was actually pre-planned from the time we originally proposed this mission. The very first sample is going to be a surface sample, and that sample will go into the TIGA instrument, and then a sample immediately to the right of that will be acquired and will go into the MECA instrument. And once we have those samples, then we plan to go back to that place where we have the first scoop, where we've revealed the white layer, and start digging down into that layer to understand what we've got there, and to better characterize what is the depth of the ice, where is the position of the white layer, how thick is it, does it go all the way to the depth of the ice table, or is it a thin layer? And then finally, once we have a better understanding of the